All right, so we've taken detailed look at solving second order linear equations that are homogeneous using power series, and we focused on solutions about ordinary points, and we've looked at different examples. We've gone through some of them very slowly, and now we're going a little bit faster. And for this next example, we're going to focus on one that has non-polynomial coefficients. And here you have to be careful, because you can't just say, well, wherever a2 equals 0 is where you'll get, are the only points that will be singular, because that assumed polynomial coefficients in your differential equation, the a2, a1, a0. Now you have this, say, cosine x, and you got to pay more closer attention to where the ordinary points would be, okay? You need this to be analytic. Turns out here, cosine x is analytic on all of R, so no problem, but you still have to pay attention, okay? If this was a natural log, we could not expand about x equals 0 will be a singular point in that case. But here it's just cosine. So in this differential equation is already in standard form, and it's a good idea, especially if you're not working with polynomial coefficients in your differential equation, that you do put it in standard form rather than just make assumptions. Okay, and so all points are ordinary here, no problem. In particular, x equals 0, which is the ordinary point we're going to get our solution about. We assume this form. Now, the only thing that sort of adds to the mix is that you gotta express cosine x in terms of power series. We are looking at power series solutions, so everything in our differential equation needs to be in terms of power series. So focusing on the left-hand side then, here's our second derivative. Here's our power series of cosine x, and here's y, okay? And multiply out the first few terms. Okay, so now we're just expanding here, and we're going to multiply the first few terms. We get this for our left-hand side of the first few terms. We combine around powers of x, okay? Now, our differential equation sets that left-hand side to 0, and so by the identity property, the coefficients of the powers of x, okay, not the coefficients c4, c2, this whole expression, this whole expression, this whole expression, that, you know, the coefficients to the powers are 0. And we could then solve these to obtain, and notice here we don't have that standard recurrence relation of ck plus 1 is equal to, you know, some mix of the lower coefficients, because that cosine x kind of messed that up, okay, if you will. But we could do this like, you know, iteratively, where we just add more and more terms if we want. Here we just it was sufficient to just go up to the x cubed term for this demonstrative purposes. So, okay, solving through, we get these first few coefficients. So, assuming this form, we have this infinite sum, you know, which is just in standard form there. And now we start making substitutions. C1 is just C1. C2 is from here, minus 1/2 C naught. C3 from here is minus 1/6 C1. And you just combine the terms that are proportional to C naught and combine the terms that are proportional to C1. Here's your Y1, here's your Y2, and you got yourself a solution. Okay, you got the two linearly independent solutions, okay, that are guaranteed by the theorem. And here I write, it may not be possible to express ck explicitly as a function of k, just as we have here. So what do we do in this case? We could have gone up in our initial expansion here to x to the 4th, x to the 5th. It's as high as you want to go, okay? So that, and make sure you're consistent with taking enough terms from each of these when you do that. So the cosine x and the rest. So you know, inconsistent here means that you'll get all the terms that are coefficients of the different x to the, so if you have x to the power 6, for example, you want to expand out such that you would make sure all the terms that are proportional to x to the power 6 after carrying out this multiplication are there. Okay, so you have to be consistent with how much you take out. And yeah, so here we don't have an explicit formula, but we have our two solutions. Now, a quick word about non-homogeneous linear second order differential equations. So we could have had a non-homogeneous term there, okay? And now an ordinary point would have to be one where px, qx, and f of x, after putting it in standard form, so you're always working in standard form for the theorem, are analytic about x naught. So you need all three of these now to be analytic. And we could extend the existence theorem to this case. And the process of solving the associated homogeneous equation with power series would be the same. Okay, so you would solve the homogeneous equation. You would do that by, just setting this to 0 for the associated homogeneous equation. You could get then the complementary function. For a particular solution, though, you're going to want to express f of x in terms of a power series. And we know we can because, well, f of x is analytic about x naught. So you would express that in terms of power series, and then you'll carry out that combination of terms, just as we've done with this non-polynomial coefficient, cosine x, okay? But you would do that with something on the other side. You'll combine terms, use the identity property, get a recurrence relation, or just as many terms as you can, as you'd like. And that's how you would solve that in case there's a non-homogeneous term there.